Hello, good morning. I'm pre-recording at least a part of today's lecture. So what I'll do is I am going to pre-record up to an hour and a half or 80 minutes of lecture, um, just in case I cannot make it to the live session because of the meeting that is uh, guaranteed to go longer than it should. Um, so So let's go ahead. We do have a homework to do today, so let's talk about the homework first. All right. So because I'm fairly sure that there'll be some questions about the homework, so that's why I want to talk about it first. All right. So the question is okay. So let's go from question number 1. Consider the not equal to relation over all integers. Which of the following relation properties apply? Okay, so let's go with the more easy ones first. Okay, so let's go with reflexive. And let me see. Okay, this is what I'll do. I am going to create a whiteboard on the side, just like the kind of usual. So this way I can kind of keep track of stuff. Okay, there we go. All right, so this is the whiteboard, and let me drag it. Oh, it's already right next to the question, so that's good. That's easy to keep track of things. All right, so I'm just typing on the side. This is for question number 1, and the first property we want to ask is it reflexive? Because being reflexive is one of the easiest relation property to check. Because in terms of being reflexive, we need every element to relate to itself. Now, can the relation contain any additional two tuples? Absolutely. But it must have two tuples for each element so that each element relate to itself. So now we want to look at the not equal to relation and ask whether integers not equal to, uh, let me rephrase it. We need to look at each integer and we ask whether each integer relates to itself using not equal to. And the answer is no. Okay, it does not. So that means, when we look at whether not equal to is reflexive or not, the answer is no. Okay, but that is really helpful because that automatically rules out partially ordered and also totally ordered, because if something is not partially ordered, it is also not totally ordered, and something cannot be partially ordered unless it has met all the requirements of being partially ordered, and reflexive is one of them. So now we want to look at transitive. In other words, if A does not equal to B and B does not equal to C, does that imply that A does not equal to C? And the answer is not. Okay, transitive is also a no. Okay, transitive. The answer is no. And let me just use an example. Yeah, the first one I'm not going to use an example because reflexive is fairly clear that an integer cannot be not equal to itself. Okay, because every integer does equal to itself. But transitive is a little bit trickier. So let me just go ahead and uh, type out why that is the case. So 13 does not equal to 15, and 15 does not equal to 13, right? So both of these are true, but it does not imply, okay? So this is going to be a right arrow. 13 not equal to 13. This entire thing is false. So that means we are now able to find a element E, element G, and element E, F, and G. Okay, so this is element E, F. This is also element F. This is element G, and element E not equal to element G is that's false. But we have true on this side. On the left hand side of the implication, this part is actually true, but this part here is false. So we have true implies false. The implication itself is false. So I have a way to find elements E, F, and G from the set of all integers such that this statement is false, and that's why it is not transitive. All right, so we got false, 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 false. The next one is symmetric. It is symmetric, okay? So we want to look at this part here and say, is it symmetric? The answer is yes, okay? Because A does not equal to B, left, right, arrow, if and only if B does not equal to A is true, okay? Because it goes both ways. Oh, that's not supposed to be Q, that's supposed to be A. There we go. All right, so it is symmetric. And now the question is it anti-symmetric? So anti-symmetric is basically saying if A or B, if A relates to B and B relates to A, that implies A equals to B. That is not true in the case of not equal to. And the best way to look at this, the easiest way to look at this is this part here. Well, not that part, but you can basically look at this being if A does not equal to B and B does not equal to A, it does not imply B equals to A. So that's why it is not anti-symmetric. So that's why only symmetric is applicable in question number 1. So obviously, to answer these questions, it is important to to read and understand and apply the definitions of all of these things. All right, so let's move on to question number 2. Consider the equal to relation over all integers. Which of the following relation applies? So we are not going to answer the question about partially ordered and totally ordered, because that depends on whether a relation is reflexive, transitive, and anti-symmetric. So we'll answer the first one. In this case is anti-symmetric. All right. So before I go any further, let me just kind of go to the definitions, because I want to show everyone where to find the definitions and also how to read the definitions. So we are now in the relations module. Okay, we go to relations, and then we go to in this case anti-symmetric. All right, so this is the anti-symmetric definition. It says, for every way to find to bind the values of E and F, so that E is an element of X and F is an element of X. So this does not preclude the possibility of E and F being the same. That's a possibility. And the actual definition, that's just a quantifier. But the actual definition is EF in R and FE in R implies E equals to F. Okay, so now we want to look at the question that we need to answer right here, which is equal to. So the question really is asking, if I find that E equals to F and F equals to E, does that imply E equals to F? Well, the answer is pretty obviously yes, okay? Because the only time, okay, if I go back to the definition here, so when you're looking at the implication, for the most part, the only tricky case is to have the left-hand side being true and then the right-hand side being false, okay? In other words, can we find a case where EF is in the relation and FE is in the relation, but E and F are not the same? And the answer is not. You cannot, because in this specific case, R itself is the equal to relation. So if E equals to F and F equals to E, that's, it kind of goes without saying that E and F are the same. Okay, so in this case, it is anti-symmetric. Now we look at reflexive. In other words, we're asking, if we look at any integer, does it equal to itself? The answer is yes. Okay, it does equal to itself. the next question is transitive. Now, transitive is it looks kind of little tricky here, but it's not, okay? Because let's look up the definition of transitive. So let me go back to the index here and then click on transitive. There we go. So with transitive, it basically means for any way of binding values of E, F, and G so that they are all elements of X. Once again, they can be the same, they can all be different, but we have to consider every single way to bind values to E, F, and G. So once again, it's an implication. So the only time the implication can be false is when the left-hand side, the precedent part of an implication is true, but the second part or the right-hand side or the consequent is false, okay? So we have to say, okay, we have to make the conjunction true first. So the only way to make the conjunction true in this case, because R itself is equal to, so that means E equals to F and F equals to G. So they're all the same. That's the only time you can make the left-hand side or the precedent of the implication true. But that means E, F, and G are the same. So that means E equals to G has to be true. So just by intuitively thinking about that, we also know that it is transitive. And it is also symmetric because A equals to B if and only if B equals to A. That kind of goes without saying. So because it has met all of these requirements, it is partially ordering. Well, okay, let me take it back. You don't need all of these in order to be partially ordered. To be more specific, symmetric is not needed is not one of the requirements to be partially ordered. So now the question is it totally ordered? Totally ordered means if you pick two things, any two things out of the set X, in this case, the set of all integers, do they relate through whatever relation we're dealing with, which is equal to? And the answer is no, okay? Because if let's just say that I pick 13 and 15, okay? 13 and 15 do not relate one way or another. In other words, 13 equals to 15, nope, that doesn't work. And then 15 equals to 13, nope, that doesn't work either. So because 13 and 15 do not relate in either direction, that fails the requirement in order to be totally ordered. And as a result, totally ordered does not apply in this case. Equal to is not totally ordered, but it is partially ordered. So that's question number 2. Moving on to question number 3. Question number 3 says, if R and S are both relations defined over X, and we also know that R intersecting with S, which means all the two tuples that are common to these two, is reflexive, then what do we know for sure about R? Okay. All right. So we really cannot tell whether R is symmetric, okay, because we just know that it has to be reflexive, okay. And that's the answer. Okay, it has to be reflexive because reflexive means every element has to relate to itself, but you can have additional two tuples in the set. Okay, so if the intersection itself is reflexive, that means both R and S contain all the two tuples so that each element of X relate to itself. Okay, that part has to be common between R and S, and as a result, R has to be reflexive. All right, moving on to question number 4. Consider the less than relation over integers. Which of the following relation properties apply? So once again, the ordering stuff, we cannot answer right away. We can only answer the other 4 first, and then depending on that answer, we can then determine whether it is also partially ordered, and that if it is partially ordered, then we can consider whether it is totally ordered. So in this case, the first one that we need to consider is reflexive, and the answer is not, okay? An element is not less than itself. And you pick any integer, let's say 4, right? Is 4 less than 4? No, okay? So reflexive is false. So that automatically, just kind of means that partially ordered and totally ordered are not true either, because reflexive is needed to be partially ordered, and partially ordered is needed to be totally ordered. So we already know that totally ordered is false, partially ordered is false, but we still have to consider the other ones. So the next one is anti-symmetric. The anti-symmetric is saying if A relates to B and B relates to A, does A and B equal to each other? And very interestingly, it is anti-symmetric. Okay, so that's kind of awkward, right? How is that possible? So let's go back to the definition, because everything has to do with the definition. So now we go back to the anti-symmetric definition. So once again, we have quantifiers on the outside, which basically just says, okay, consider every single way to bind E and F, okay, to as elements of X. That part we have explained already. Just look at this as a double loop, okay? One loop for E and one loop for F. So that E can go through all the possible values in X, and F can also go through all the possible values of X. So the real question is about this implication, okay? It's about whether we can make this implication false or not. If we can find one case to make this implication false, then it is not anti-symmetric. On the other hand, if we say that's not possible, okay, this implication is always true, then it is anti-symmetric. So in order for this implication to be false, we need this conjunction to be true, because if this conjunction is false, false implies whatever is always true. The implication itself is always true. So we need to make this conjunction false. We need to make this conjunction true, which means EF is in R and FE is also in R. Now remember, R in this case is less than. So we need E to be less than F and F to be less than E. That is just not possible, because you cannot have an integer being less than another integer and the other way around is also true. That's just not possible. So that means this conjunction is always false. Okay, if this conjunction is always false, that means the precedent for the left-hand side of the implication is always false, which means the implication itself is always true. That is why it is anti-symmetric. We already know it's not partially ordered, so let's look at symmetry here. Is less than symmetric. In other words, if A is less than B, if and only if B is less than A, is that true? That is absolutely not true, right? Because in order for if and only if to be true, both sides have to be the same. Okay, so either it is true true or it's false false. And we know in this case it is not true, because A is less than B means B is not less than A. Okay, so we can only have one side being true and not both sides being true, and as a result, it is not symmetric. Transitive is a yes, okay, because if A is less than B and B is less than C, is A less than C? The answer is yes, it is. So question number 4 has these two particular items checked. I'm getting some traffic on Discord. Okay, it's not, okay, it's all right. I don't need to respond to that right now. Okay, here's question number 5. Question number 5 says, consider the greater than or equal to relation over integers. Which of the following relation properties apply? Okay, same thing, right? But this time it's greater than or equal to. So let's look at symmetry. It is not symmetric. A is greater than or equal to B if and only if B is greater than or equal to A is not true. Okay, all you have to do is to find one counterexample. So if I say A is 13 and B is 15, then you can see how the if and only if does not work, because in this case, let's say, so A is greater than, 13 is greater than or equal to 15 is false. Now, that doesn't mean the if and only if is automatically false. We just need the other one to be false. But the other one is not false, because 15 is greater than or equal to 13 is actually true. So we have false on one side and then true on the other side of an if and only if, which makes the if and only if false. Now, we just found one case, right? One integer is 13 and the other one is 15, but that is all it takes in order for a universal quantifier to be false, because the whole idea of a universal quantifier is that whatever statement is that the quantifier is applied to has to be true for every single case. So it's not symmetric. Is it transitive? Yeah, it is transitive. If A is greater than or equal to B and B is greater than or equal to C, does that imply A is greater than or equal to C? The answer is yes. Okay, it is transitive. We cannot quite answer the question of whether it's partially ordered, because just being not symmetric is not enough to disqualify as partially ordered. So now we move on to reflexive. It is reflexive, okay? Even though there's a greater than here, but there's also an or equal to, right? So for any integer, okay, let's pick a particular integer. Let's pick 14, okay? So the question is 14 greater than or equal to itself? Yeah, 14 really is greater than or equal to itself, so it is reflexive. We can't answer totally order yet. Let's answer the question of anti-symmetry. Okay, is it anti-symmetric? In this case, it is anti-symmetric, because if A is greater than or equal to B and B is greater than or equal to A, what does that tell you? A and B have to be the same. So A is greater than or equal to B and B is greater than or equal to A does imply that A and B are the same. So it is anti-symmetric. Now, because transitive, reflexive, and anti-symmetric are all true, now we have to think about, now we know it is partially ordered, but then we also have to think about, is it totally ordered? In other words, if I pick any two integers, okay, let's call these two integers A and B, is it true that either A is greater than or equal to B, or B is greater than or equal to A? Okay, now let me rephrase it. I used the wrong phrase. Instead of using either or, it is just a regular or. So let me just rephrase the whole thing. For every way to pick two integers out of a set. All right. Okay, I take that back too, because that's not the right way to say it. For every way to bind two variables, one is A, one is B, to an integer, okay, is it true that A is greater than or equal to B, or B is greater than or equal to A? Now, there's a regular or, which means they can both be true at the same time. If I had used either or, then only one can be true at any particular time. But both can be true, but at least one is true. The answer is yes. Okay, if you pick any two integers, A and B, it is always the case that A is greater than or equal to B, or B is greater than or equal to A. Now, in certain cases, both are true, because if A and B are the same, then A is greater than or equal to B and B is greater than or equal to A are both true. But we don't need both of them to be true. We just need at least one of them to be true. And that really is the case for greater than or equal to. So that's why greater than or equal to is also totally ordered. All right, moving on to question number 6. If R is a relation defined over X, is known to be reflexive. So we know that R is reflexive, but not anything else. Which of the following do we know for sure, regardless of the actual definition of R and X? Okay. So we can see that these are all based on relations between the cardinality of R versus the cardinality of X. So we have, R is greater than, the cardinality of R is greater than or equal to the cardinality of X. That seems to make sense, right? Because, for every element of X, there has to be an element of R corresponding to it, because it is already known to be reflexive. So we go like, maybe, okay, we check it first. Not equal to, nah, that cannot be true, because it doesn't guarantee that it's not equal to. Because if R is really just reflexive and not anything else, okay, let me put it in a different way. If R is the minimum relation, so that it is just reflexive and symmetric at the same, just reflexive, and doesn't contain any other elements, that are unnecessary for being reflexive, then R, the cardinality of R does equal to the cardinality of X. Okay, so we cannot guarantee this. And for the same reason, we cannot guarantee this either, because R can contain additional two tuples and remain to be reflexive. Okay, so we cannot tell that they are the same. The fourth one is absolutely not true, because if the cardinality of R is less than the cardinality of X, we know for sure that R is not reflexive, because it is definitely missing a two tuple for at least one element in X. Since we already know the first one is true, so that means none of the other answers can be confirmed. It's going to be false. So only the first one is correct. So I think this is the last one. The last one says if R is a relation defined over X and R is known to be symmetric, which of the following do we know for sure, regardless of how R and X are defined? So once again, we are looking at the cardinality in this case. Okay, so now we have to kind of think about symmetric, right? Symmetric is kind of a tricky one, okay? Because let's look at each one and see if that is guaranteed, okay? The cardinality of R does not equal to the cardinality of X. That cannot be guaranteed, okay? Because if R is the minimum relation in order to be reflexive, then their cardinalities would be the same. But if R is minimally reflexive, then it is also symmetric. So we have ruled this out. The cardinality of R is odd. Nope, definitely not true, because there's no guarantee, okay? You can Okay, the easiest way to illustrate the cardinality of R is not guaranteed to be odd is an empty relation is automatically symmetric. Okay, so we know the cardinality of R cannot be guaranteed to be odd. The cardinality of R equals to the cardinality of X. Well, that cannot be guaranteed either. Okay, because let's just say that X has 1, 2, and 3. Okay, and R can consist of only one single element, which is 1, 1. Okay, that would make it symmetric. Non-reflexive, but symmetric. But the cardinality is definitely not the same, because X has 3 elements and R only has 1 in this case. Also, if you look at R as an empty relation, that also fails this requirement, because regardless of the number of elements in X, R has a cardinality of 0. All right, so let's look at the next one. It has to be a even number at least, because 2 times the cardinality of X has to be an even number. We know this is not true, because we can make the cardinality of R an odd number, okay, or just 1. So that is not true. The cardinality of R is even. Same reason, it's not true. The cardinality of R is greater than or equal to the cardinality of X. That is also not true, because R can be empty and X can have as many elements as we want to put in it. And then we have the cardinality of R being less than the cardinality of X. That cannot be guaranteed either, because if you think about R being marginally or minimally reflexive, and then we just add 2 more elements, okay? That makes it, that makes the cardinality of R greater than the cardinality of X. Or in this case, just minimum, okay? Just think of R as the minimum relation in order to be reflexive, okay? That will make R and X having the same number of elements. So the number of elements of R is not guaranteed to be less than the number of elements of X. So the only choice is to answer none of the other choices can be confirmed. So let me check whether I got everything right or not, because if I don't, then I have some explaining to do, don't I? Okay, so let's check. 1 of 1, 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 and 1 of 1. Woohoo! I got 7 out of 7. Well, if I don't, okay, I think I'm in serious trouble. But occasionally I do make a mistake or two and not get a full score. Cool. All right, so if you're watching this part and you're having some questions and you want to kind of present a specific case, for a particular question, you can go to the text channel of today's lecture and just kind of give me, state your question. So this way, if I cannot rejoin the class in time, hopefully other students can kind of talk about it and maybe get an explanation. If not, okay, if I look at the text channel and nobody is stating the correct answer or stating the correct explanation, then I'll go ahead and jump in and state the answer to that question. There's no need to use LaTeX in this case because braces and the notations that we are familiar with, they can all be done without LaTeX. So you can just go ahead and type braces, parentheses, and stuff like that. All right, so I am going to move on to other things. The only really important thing that I want to kind of re-emphasize at this point is basically to re-emphasize that it is important to understand these definitions. And these definitions, let's pick one that is a little bit tricky, which is anti-symmetric, okay? They're all based on, a lot of these, not all, because reflexive is not based on implication, but a lot of these are based on implication or equivalency. Okay, equivalency is kind of like implication, but it goes both ways. But in this case, the implication only goes one way. Okay, so it is extremely important to understand what is implication. Implication, all it means is there's a truth table to look up to find out what is implication, as a Boolean operator. So the best way to look at implication is not to think about its semantic, is not to think about the meaning of implication in normal English conversation, but to look at implication as an actual Boolean operator, just like logical and, logical or, and so on, except this one is not commutative, okay, which means A implies B does not always imply B implies A. Whereas A and B, okay, is always the same as B and A. So that's the only part, that is a little bit tricky about implication, but nonetheless, it is really just an operator, okay? And remember, for that operator to be false, the left-hand side has to be true, the right-hand side has to be false. That's the only time an implication itself is false. That is really, really important, okay? All right, so I am going to move on to, well, actually not to move on, but to get back to the topic that we had started already. And there's plenty more to go in propositional logic. So now we're going back to propositional logic. And I'm just looking at the time to make sure that I stop the recording and upload it at the right time because I don't want to miss my meeting starting at 10 o'clock. All right. And you guys can tell what time it is right now because it's in the recording itself. All right. So we're back to propositional logic and we have already started with resolution. So let me just kind of recap what we have already talked about. This is a proof, okay? This is a proof, that shows that this entire expression is always true. Then it goes like, okay, why is that important? Well, it is important because this implication is always true, which means if you can find me two disjunctions, and the two disjunctions, they do not share, okay, because it is not the same. But if one part of one is psi and the other one has the negation of psi in the disjunctions, then they quote unquote cancel out. Okay, not exactly cancel out, but they act as a connector, so that the psi and not the psi not psi part is out, and you're only left with phi and rho in the disjunction. Okay, Now this is really, really important because we can start with 3 components and we end up only with 2 components. So you can kind of see this and go like, hey, if we keep going like this, it is possible that we might end up with nothing, okay? Which is actually the goal, okay? So this mechanism itself is called resolution. And because we can prove this implication to be always true, then we can turn it into a transformation rule that is an element of zeta, okay? So later on, we can see that we put this into zeta as the only rule. And of course, I have to go right here. Okay, so this is how it looks like as a transformation rule. In other words, in this case, every single well-formed formula looks like a disjunction of some kind. Okay, so in this case, because phi, well, actually every single Greek symbol can be an expression itself. So this phi can be not just one single variable. It can be, P or Q or R, okay? And then this row here can be not P or Q or not R or something like that, okay? It doesn't matter what they can be, but we can basically look at each Greek letter and basically just say it's a placeholder of something that can be bigger than just one single symbol, okay? It's just a placeholder. Phi, not phi in this case, the phi itself is the same, okay? It can be a variable, can be an expression. But because of the way we define well-formed formulae, which is outlined down here, we know that psi, this is psi. So we know that psi cannot be more than just a variable or the negation of a variable, because if it is anything more than that, then we would have failed the qualification to be a well-formed formula for this disjunction or for this disjunction here, probably for the other one. But psi has to be either a variable or the negation thereof. Okay, so we talked about this part already. All it says is a well-formed formula under quote-unquote new management has to be a disjunction, and inside the disjunction, every component inside disjunction can only be something from alpha or the negation thereof. Okay, so each component inside the well-formed formula cannot be I have to find the right word to say it. It cannot be, there's no conjunction for sure, because conjunction is not even in omega. And at the same time, it cannot be the negation of an or, because it has to be something that is the either something from alpha or the negation thereof. So we talked about this last week, and I gave several examples of what is and what is not well formed under this new management. Section 5.2, we touched on this already last week as well. It really is asking, okay, if you just give me some random Boolean expression that is quote unquote correct, okay, can we always convert that can we always convert that Boolean expression into a conjunctive normal form? So a conjunctive normal form has a very kind of specific format. A conjunctive normal form is the conjunction of this. Okay, look at it this way. It is a conjunction of a well-formed formula or well-formed formulae under this new management style. Okay, so if you just give me a bunch of well-formed formulae under this new qualification, then the conjunction of those well-formed formulae will be considered a conjunctive normal form. So the full definition of conjunctive normal form, or CNF, is defined here. So I'll just kind of quickly go over this. Note that all produced inferred well-formed formulae and every element in I are implicitly connected by a conjunction. So everything that is known to be true are connected by conjunctions. As a result, what is known to be true is essentially a CNF or conjunctive normal form, where the overall operator is a conjunction, which is the last operator, the topmost operator, and all components in the conjunction are themselves disjunctions. Each disjunction can only consist of elements in alpha or negations thereof. Okay, so that is a really kind of restrictive way of looking at things, right? Because that means we're imposing a very big restriction on how we can express everything in this system. Okay, so CNF. Okay, so let me just kind of talk about what a CNF is. I just want to give you guys some examples. Okay, so this is for CNF discussion. So the first thing is, we want to define alpha. So let's just define alpha to be 0, 1, P, Q, R, S, T. The Greek symbols are supposed to be here as well, but the Greek symbols are only useful in a transformation rule. So as a result, we don't, they're not important in this discussion. So we'll just go ahead and say that they are the ellipses. Okay, so we have dots as, oh, there we go. Okay, so this is our alpha. The curly braces is not showing up because curly braces by themselves have meanings in LaTeX. So that's why when we want to show the ellipses, when we want to show the braces, we have to use a backslash to escape them first. Okay, so let's say this is how we define alpha. So the next question now is what is considered CNF. Okay, so we'll go ahead and show a few examples. And I'm also going to use a shorthand so I don't have to keep typing the conjunction symbol and also the disjunction symbol. So I'm going to use, I'm going to borrow the notation of multiplication to mean conjunction, and I'm going to borrow the notation of addition to mean disjunction. Okay, so in this case, P not Q R or QR is in CNF. Actually, I just lied. Okay, I'm a big liar in this case because these have to be conjunctions, and this one has to be a conjunction, and these have to be a disjunction also. So this is now in conjunctive normal form. Okay. Another example. Okay, so I'll show you what is considered CNF. Q by itself is in conjunctive normal form. Okay. And 0 is in conjunctive normal form. Let's see. Okay, so I think these are very good examples as conjunctive normal forms. And here's another one. Okay, just so that we can say, make sure that it is clear. So if I have a simple disjunctive form, a disjunctive element of P, another one as Q, and another one as R, this is in conjunctive normal form because each one, P is a disjunctive term, Q is a disjunctive term, R is a disjunctive term. Okay. Now, if you're not really convinced that Q by itself is a disjunctive term or 0 by itself is a disjunctive term, it's easy to convert it into a disjunctive term. Okay, so let me just do this trick here. Because Q or false is a disjunctive term. Now, if you want to say, but I don't see any conjunction here, well, guess what? You can always have a conjunction with true without changing the meaning of anything. So now it looks kind of like a regular conjunctive normal form where the overall operation is a conjunction. This is where the conjunction is, and every single term is a disjunction. And then somebody's going to say, yeah, I can see this is a disjunction, but what about this one over here? Fine, okay, we can do the same trick. Now it is disjunction, right? But it doesn't really change the meaning. Okay, so what what we can see as Q all by itself can now be turned into a, what we normally see as a conjunctive normal form, where we have a conjunction of disjunctions, and then inside each disjunction we only have symbols that are in alpha or negations thereof. Okay, but if you ask what is the if you compare this expression with this expression here, you will find that they are exactly the same regardless of the value of Q. Okay, so the same thing applies to just false by itself, because false by itself doesn't seem like it is a conjunctive normal form. So let me make it into something that looks conjunctive normal form. Okay, so we can now say, what about this? Okay, so false, okay, is false or false. Okay, false or false is just false, right? And whatever we have here, okay, you can always say and true. Okay, but true is also known as true or false. So now it looks like what we're expecting, right? Because in a conjunctive normal form, the last operation has to be a conjunction, and what it is joining by conjunction, what it is anding, are disjunctions. So we got a disjunction here, we got a disjunction here. So now it looks proper, right? And also for the same reason, this is just P or false, Q or false, R or false. Now the or false is usually not specified, because it is just using extra space and not really doing anything. But there are occasions where, if you say, okay, but it is not clear to me that P is a disjunction by itself. Yes, it is, okay, because we can always say or false to anything and preserving the meaning of that thing. All right, so what is not conjunctive normal form? Okay, so let's give some example of what is not. Okay, so we'll say, let's see, P or the negation of Q or R. And then I don't know, let's say not R, okay, is not in C and F. It is not in conjunctive normal form, because the final operation is okay. It is just an AND operation here. But when you look at this disjunction, it looks okay, right? Everything is being connected by a disjunction. But the problem is this negation can only be applied to a single element in alpha. But in this case, it is applied to an expression. Even though this expression has a disjunction in it, it's not good. This is no good, okay? Because this negation can only be applied to a single thing in alpha. And when you look at what it's applied to, this portion here is definitely not something that you find in alpha, because alpha has Q as an element, alpha has R as an element, but Q or R is not an element in alpha. Okay, so that this is not a conjunctive normal form. All right, so now we are, I'm showing some examples of what is considered a conjunctive normal form. So now the question is, really, can we convert every legitimate Boolean expression to conjunctive normal form? The answer is yes, okay? So when we look back at the notes, which is here, there's a particular example, which is section 5.2.1. So this is the original expression, and by using Boolean algebra, we can find that, oh, yeah, so we can actually define it using a as a conjunctive normal form. So this is actually part of your homework assignment, and let me just go ahead and release it now. So your first homework assignment is to convert an expression into its conjunctive normal form. So let's go to the homework. So let's see, this is the homework assignment, CNF. And what you have to work with is this one here, okay? This is a legitimate Boolean expression, but I want you to convert it into CNF, into conjunctive normal form. Okay, so let me go here and release the assignment. So this way you guys will have a chance to practice. I will give you guys unlimited attempts. It's only collecting the answer as a text entry. So you don't need to use LaTeX, and you can just use the shorthand that I have used using exclamation point as negation. What looks like addition is disjunction, and what looks like multiplication is conjunction. Okay, so that's why I will let you guys use text entry here. And the due date is going to be in a week. Today is the 13th, so the due date is going to be the 20th. So October 20th at the beginning of start time, which is 10:30 a.m. And there we go. And my suggestion is to get this started as early as you possibly can. Okay, that's just important. And guess what? I'm gonna go here and change this equation just a little bit, because I like to change things up a little bit from time to time. All right, so we'll throw some negations in to, you know what? I'm not gonna change it. We'll just leave it the way it is. Okay, so we'll leave it the way it is. And remember, a homework assignment is really a chance for you guys to practice. So people who want to find the answer of a homework assignment in an easy way, they're not really cheating anyone but themselves. Because in an exam, and I ask about something like this, anyone who has done the homework assignment would have learned something, okay? Would have learned the techniques, would have a chance to practice the techniques and whatnot. And people who find a shortcut to type in the answer of the homework assignment may get a few points, really quick and easy. But when it comes to the next exam, those people would not be prepared. So I suggest that everybody work on this individually. Don't ask another person unless you have given it at least a day. Okay, if you have looked at this for 15 minutes and you have no idea how to proceed, that would not be a good time to start asking another person. Am I going to stop you? No, there's no way I can actually stop you. Okay, I shouldn't say you, but there's no way I can stop someone from asking another person how to do something like this only after spending 15 minutes on the question. But let's just say that that is not recommended. Okay, my recommendation is to kind of really think about this, digest it for about a day. Okay, on the second day, if there's no clue of how to proceed with this one, maybe ask someone, including myself. Okay, I would answer questions. Okay, no, let me take it back. I would not necessarily answer questions, but I would respond to questions. There's a big difference between the two, because sometimes I respond with another question. Okay, so that is important. Okay, cool. So I'm going to release it, save and publish. There we go. So now we have the homework that is due in a week. And once again, get started with this one early, because it is not an easy one. Okay, it's not going to be an easy one, but you have to start early. All right, so now we go back to how do we do this, right? How do we convert something into CNF? So there are certain guidelines here. Okay, so let's go through this guideline. So if the top level operator is an OR, okay, which is basically saying blah 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 or blah 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 is given to you, then what you need to do is to look at all the components of the OR. So this notation here, which is phi equals to the big OR, where I goes from 1 to n of psi of I, all that is saying is each psi I is a component of the overall OR. So now you want to consider, what about each psi I? Okay, So if each psi I is a disjunctive element, then you're done already, because in that case phi is already in Cn, is a well-formed formula by itself. Okay, so you basically just join all the components, dissolve all the parentheses, and we're good to go. Okay, in other words, phi in this case is one gigantic disjunctive term, and since it is a disjunctive term and it's by itself, it is also well formed. So if this is not the case, if this quantifier itself is false, which is most likely the case, because otherwise you have a pretty easy one to work on. So if that is not the case, then you want to see if then you want to look at each psi I and find out what it is. If psi I is a negation of either conjunction or disjunction, then you want to apply De Morgan's law, because what De Morgan's law is doing is you can look at De Morgan's law as a distribution, but it's not the same as a distribution like A plus B, the whole thing times C is AC plus BC. It's not that kind of distribution. It's distributing the negation to the nested portion of an operator. And because the negation of an operator is a big no-no in CNF, so we want to distribute that negation all the way in so that negations are only applied to elements of alpha. And that's why De Morgan's law is really helpful in this case, because whenever you see a negation of either conjunction or disjunction, use De Morgan's law, okay? Because that will distribute the negation to the nested components, okay? If psi I is a conjunction, then you apply distribution. In other words, if it's a conjunction of something, then you apply distribution. Now, what if it's a conjunction of just regular terms? Okay, then you apply the other rules, because now you can see if the overall operator, the top operator, is a or, then you want to if the overall operator is psi or rho, okay, so the top operator is an and already, then you want to break them up, okay, so you want to evaluate psi as the next target to turn into a CNF, and you want to look at rho as the other target to turn into CNF, and then reapply the technique recursively. Because once you turn psi into its own CNF and you turn rho into its own CNF, then joining two CNFs using conjunction is a-okay. Okay, so if psi is already a CNF and rho is already a CNF, the conjunction of two CNFs is by itself a CNF. So this rule here is basically saying recursively apply these techniques and consider psi as your new phi, and then you consider this rho as your new phi. And basically, it's just a recursive way of reapplying the same technique. And this is kind of why CISP440 is really useful as a co-requisite, because by now, CISP430 should have talked about recursion or the concept of recursion already. And guess what? We need to use that concept of recursion to understand what this instruction is saying. If the top operator is a negation, then there are three possibilities. So if it is a negation, that means the thing that we want to turn into CNF, which is represented by phi, is the negation of something. Okay, that something is now known as psi. So now we want to say, okay, what are the three possibilities? The first one is psi is an element of alpha. Then we go like, oh, okay, we're done already. The next one is, what if phi is a conjunction? So we have the negation of a conjunction. Then we apply De Morgan's law. What if psi is a or? In other words, we have a negation of a or. Then we also apply De Morgan's law. Okay, and you can see how after we apply De Morgan's law, we end up with a we still end up with a disjunction or conjunction, but you can see how the outer negation, which is this one here, is now quote unquote distributed to the components of the original operator. So we are basically moving the negation deeper and deeper until we only apply negations to elements of alpha. Okay. Obviously, there's also a simplification step where the negation of a negation cancels out. Okay, so that part is really kind of easy to understand. I'm just looking at this, and there's one thing that I need to look at here. All right, so it is this particular one. All right, so let's take a look at this one here. The top operator is an OR, and inside the OR, each psi I is not well formed. In other words, each psi I is not a disjunctive element. So that means by the time we hit this portion here, psi I is not a disjunctive element. Now, if psi I is not a disjunctive element, there are only a few possibilities. If psi I is not a disjunctive element, which means it's a disjunction of things from alpha or negations thereof, okay, there are only a few possibilities. It is psi I itself is a negation of something. Then we apply De Morgan's law. But there's the other possibility is psi I is a conjunction. Then we apply the distribution law. And I'm just thinking that there are some other possibilities. If it has conjunctions, then you apply distribution. Because I think this part needs to be applied recursively. This is a general strategy. So the actual conversion may involve more tricks than is encoded here, but they're all based on Boolean algebra rules. Okay, so I think it's a good idea probably to talk about those rules in order to convert something into CNF. So CNF conversion rules. These are basically just Boolean algebra rules. So you can look at this exercise also as an exercise of Boolean algebra. Okay, we can talk about simplifications first. So we can say, x, is any type of expression. Let me just kind of, we'll use x as a general expression. So if I have an expression and true, okay, it is just x itself. Okay, remember what looks like multiplication is a conjunction. This is a disjunction. That is also just x. So these two are for simplification. And the distribution goes in two ways. Okay, so we have x plus y z. That is xz plus yz. That's one of the distribution. This one looks familiar because it is the same as the normal algebra distribution. But the other one is, it looks awkward because that's not how, this doesn't work in normal algebra. So in this case, it is x plus z and y plus z. So this is also distribution in Boolean algebra. Then we have the De Morgan's law, which are extremely useful. So the negation of a conjunction is the negation of each component of the conjunction, and then you change the operator of the conjunction into disjunction, but you can move the negation into the components of the original conjunction. And the other way around is also true when we have the negation of a disjunction. So that becomes the negation of the components connected by a conjunction, like that. Then we have another, simplification. The negation of the negation of something cancels out, and it's just that something originally. Let's see. Oh, we have implication. Okay, so x implies y is the same thing as not x or y. Okay, that's one way to. That's basically how implication is really defined. It is the negation of the precedent or the consequent. Let's see. If and only if. Okay, so if x if and only if y is the same thing as x implies y and y implies x. Okay. Let's see, am I missing out anything that is important? There's more simplification. Anything and false is false. Okay. And then anything or true is true. There's also commutative law, which is x or y is the same as y or x. And it applies to conjunction as well. X and y is y and x. So those are fairly familiar. Okay. And you can see that there are certain many of these rules in Boolean algebra, or many of the axioms in Boolean algebra are the same as the ones in normal algebra. Some are kind of awkward, okay, and I can star the ones that are kind of strange, okay. So this one is unique to Boolean algebra. If you compare Boolean algebra versus normal algebra, this one is unique. De Morgan's laws are definitely unique. Algebra. This is also unique to Boolean algebra. This one is not really so unique, okay? Because if you look at logical negation as arithmetic negation, that is something that we find in normal algebra as well. Implication is unique to Boolean algebra. This one, or if and only if, is definitely unique to Boolean algebra. Oops, cannot spell. Algebra. There we go. X times 0 is 0 is also true in normal algebra. This one, the OR is unique to Boolean algebra. Commutatives, they are not unique to Boolean algebra because normal algebra have those as well. So we can see that there are certain things here that are common between Boolean algebra and normal algebra, and certain things that are not, common. Okay, so I just want to point out the ones that are not common, so that you guys pay more attention to those things, because they're not usual. Okay, they are not something that you are familiar with. So now this is already enough to have FOIL. Okay, so FOIL is not one of the axioms. Okay, so let me illustrate what I mean by that. So let's say you have x or y, or w or x on one side, and then y or z on the other side. I don't need a special axiom to do this, okay? Because I can just apply distribution twice, okay, or at two different levels to get this done. The first level, okay, if I use distribution, which is here, okay, so this is the distribution law that I'm going to use. So I'm going to distribute the left-hand side over the right-hand side. So that would become W and Y or Z, and then the whole thing or X and Y or Z, okay? But if I use commutative law, then now I can distribute Y or Z over W and distribute Y or Z over X. So now I apply distribution one more time. So I end up with W and Y or W and Z or X and Y or X and Z. So in other words, what we know as FOIL is really just coming from distribution, but applying it twice, okay? And I'm going to give you guys this as another example. So if I have A plus B plus C times D plus E plus F, you can kind of see that this is the same thing as a Cartesian product, where you end up with A and D, or A and E, or A and F, or B and D, or B and E, or B and F, or C and D, or C and E, or C and F, right? Because we just have one more level, just like in the previous case, except we have one more level of application of the distribution law. Okay, so I'm not spelling out everything here, but I'm spelling out all the simple ones. And by reapplying the simple ones, okay, you can basically get to the more complicated ones. Okay, so these are the ones that you should keep in mind when you're doing a homework assignment. The simplifications are very, very important. Oh, I forgot a few. Okay, talking about simplification. So another simplification is if you have X or X and Y, that really just boils down to X itself. Okay. And then if you have the other way around, which is X or Y, okay, I should say X and X or Y, that really just kind of boils down to X as well. Okay, so the first one, so both of these are unique to Boolean algebra, unique to Boolean algebra. And this one is also unique to Boolean algebra. Okay, so I can just kind of briefly explain. I mean, you can prove this using a truth table. Okay, you can just have a 4-entry or 4-row truth table to prove this. But intuitively, it makes sense because X is one particular value, and X and Y is a more specific value. In other words, if X is true, I'll take it back. If X and Y is true, X is going to be true regardless. But when X is true, X and Y is not necessarily true. So I can basically just eliminate X and Y and just, because it doesn't really add anything to the disjunction. The other one, it kind of works the same way, but except it's kind of opposite. Because X is the more restrictive term compared to X or Y. What that means is if X is true, X or Y is guaranteed to be true. But when X or Y is true, it does not guarantee that X is true. So X or Y really doesn't add anything to the overall conjunction. Okay, and I will give you two more things, which is operator priority. Okay. So negation goes first, okay? So when you have a negation of something, it takes top priority. So when we have not X or Y, it really is applying the negation to X first and then do the or Y. And it's the same thing in the conjunction. Not X and Y is just not X first and Y. So that's operator priority. And then we have operator priority between the and versus the or. So x, y, or z is first applying the conjunction x, y, then apply the disjunction or z. That's basically just normal. Okay, that's how we look at that's the same operator priority as in normal algebra. So I think that covers all. Okay. Yep. So I think that covers everything that we need in order to do the homework. The simplification rules are really helpful. You should simplify as much as possible after each step, because otherwise this assignment can end up with a huge number of terms. Okay, so you want to be able to apply the simplification rules as much as possible. Simplification, all it means, there's another one. I keep forgetting, the x or not x is true, okay, and then x and not x is false, okay. That kind of makes sense, but these are also unique to Boolean algebra. There we go. It kind of makes sense, right? Because between x, not x, exactly one has to be true. So in the disjunction, if at least one side is true, the whole thing is true. But you can also say that between x, not x, at least exactly one is false. So in the conjunction, if at least one is false, the whole thing is false. So that's why we have these two rules as well. They're also for simplification. So what simplification is really meaning is you start with more things and you end up with fewer things. You start with more things, you end up with fewer things, right? Distribution, can also be looked at the other way, because when you look at it from this side first and then you end up with this side, it is factoring. Okay, so factoring can be helpful. Generally, that is not the case when you convert something into CNF, but occasionally you might find it useful. And you can also apply factoring here as well. When you see this, then you can factor it into something that looks like this. So it goes in both directions. All of these are equal symbols. They're not implication, which means you can start on one side and then go the other direction. So don't restrict yourself from looking at things only from left to right, because the equality goes from right to left as well. Okay, I don't know why you want to go from right to left in some of these cases. Like if you start with x, why would you want to use double negation on top of that? There are very few cases where that is actually a good thing to do, but not a whole lot. Okay. So the other some of these simplification rules are really kind of important to remember, because they are not found in normal algebra. Like these two are particularly helpful, because once you convert something to either true or false, then you can apply the other simplifications. The other simplifications, like this one, the other simplifications like this one. So it is really helpful to be able to notice something like this. And something like this can be done, okay, after you apply distribution. Because after you apply distribution, you might find that you have a term and the negation of that term in the same disjunction, or that term and also that term in the disjunction, okay? And you also don't forget that you can apply the commutative law, which is changing the ordering. So you can basically apply that. Oh, okay, there's another one that I keep forgetting. It's associative, okay? But that's also found in normal algebra. So x plus y plus z is the same thing as x plus y, then the whole thing plus z, which is also the same as x plus and then y plus z. Oops. Okay, so that's known as associative law, which is in normal algebra as well. And multiplication works exactly the same way. X and y and z is x and y first, and then the and z, but it's also the same as x and the conjunction of y and z. Okay, so we know these already from normal algebra, but I just want to restate it here, just so that you guys have an idea of what is also applicable. Yep. So between all of these, that's what you need to use for the homework assignment. I know it sounds like a lot, but many of these rules you already know, okay? Like associative, commutative, one of the distributions, and some of the identities you already know, okay? So the ones that I marked here as unique to Boolean algebra are the ones that you are probably not familiar with yet, okay? So you want to pay attention to those. All right, so let me see, what time is it? Okay, it's 9:53. Okay, so your homework assignment is already up, okay? And I just want to spend the last few minutes here to talk about the overall where we are, because I just gave you a whole bunch of pine needles, okay? These are pine needles. So I want you to kind of go back, kind of take a step back and look at the entire pine tree or even the pine forest, okay? Because what we are doing here is we are now you're trying to learn how to convert any Boolean expression into CNF. And the reason why we like CNF is that is how we can apply resolution. So now the question is, knowing what is resolution and being able to convert everything into something that resolution can work on, then what? Okay, that's the very last element of this entire thing, and it has to do with proof by contradiction. So besides working on the homework assignment, you have a week to do it, okay? But you want to start early so that you can have time to ask questions before it is due, okay? I would prefer people to work on something as early as possible, so that I don't get a whole lot of questions the evening before the due date of an assignment, okay, which I tend to get for some reason. But proof by contradiction is also something that I want you to read ahead. And this is for Thursday, okay? Because on Thursday, we are going to focus on proof by contradiction. And the whole section starts with a proof again, okay? Well, this is not actually a theorem. It is known as a corollary, okay? Corollary. Okay, I have to practice the pronunciation of this one. But what it is you can look at a corollary as a small theorem, okay? It's not big enough to be coined a theorem, but it is important nonetheless, okay? So all this is showing is P implies Q implies P and R implies Q and R is always true. In other words, if you already know that P implies Q is true, you can always add a conjunction or always add via conjunction something to both sides of the implication, and that new implication is guaranteed to be true as well, given that P implies Q is already true to begin with. And then from that one, we basically look at the actual mechanism of proof by contradiction. And then at this point, okay, between up to section 5.4, right before 5.5, then we have all the three components. There are three components that we need for automated theorem proving using propositional logic. One is CNF, okay? The ability to convert any Boolean expression into CNF. That's the first one. The second one is resolution, because resolution only works on CNFs, okay? The third one is proof by contradiction, because as you apply resolution, you will end up with two particular results, okay? In a finite amount of time, you end up with one of two conclusions. One is you have a resolution, you resolve everything down to a 0. So if a CNF, a conjunctive normal form, has one component being a 0, then the whole thing is going to be false, right? Or you can end up with something that you say, we cannot apply resolution any further, okay? Every way of applying resolution to all the different terms inside the CNF is already done, okay? We cannot resolve to any new term that we have not seen yet. And yet, false or 0 is not one of those things inside this particular CNF. So you would arrive to one of these two end states. If you arrive to the end state of, yes, we can see that false is a component of the CNF, then using proof by contradiction, you can conclude that, I forgot one of the things, because in proof by contradiction, you have to negate the theorem first, but by arriving to a 0, you can now say that the theorem is true. Okay, it follows whatever is given to you. Okay, it follows. But if you cannot get to a 0, that means whatever that statement is not a theorem, meaning that it does not follow from whatever is known to be true to begin with. Okay, so that's a lot to take in. Okay, because you need to. So right now we are diving into the pine needles of CNF. Okay, then we need to zoom back out to look at, and then zoom back in to the pine needles of proof by contradiction. Then we need to zoom out 2 levels, okay, because we have resolution, CNF, and then proof by contradiction. So at that point, once we have all 3 pine trees explained, then we take a step back, look at the 3 pine trees and say, okay, what do these 3 pine trees have to do with theorem proving in propositional logic? That is what 5.5 is about. Okay, so it's extremely important that you read ahead of me, so that at least you know what the term proof by contradiction is, and you can see the theorem itself, and also at least the general strategy of proof by contradiction. So that's kind of what I want you guys to do for Thursday, and then plus the homework assignment, which is due next Tuesday. All right, so I'm going to stop recording here, and I will post the this particular spreadsheet, not spreadsheet, the whiteboard, into Discord. But I have to go for the meeting at this point. But I will still be able to do something on the side, okay? But I cannot continue the recording anymore. So hopefully I get to see you guys live at some point today, and if not, this is kind of the async. So today may be asynchronous only, depending on how much time I have after the meeting.